Hello there again. How nice would it be if you were able to compute the values of complicated numbers like the sine of pi divided by 8 or the cubed root of 11 without using a scientific calculator? We can do using Taylor polynomials. So what is a Taylor polynomial? It is a generalization of the concept of a linearization, which we discussed in the previous video. The idea is to approximate the value of a general function at a point by another simple function. This simple function is a polynomial function. As we can see, when we are close to the point A, the approximation is good, but when we go a little further away, the discrepancy between the values of the function and the linear approximation quickly gets bigger. One of the reasons for this is that a straight line doesn't follow the twists and turns of the graph of the function f. So let's try an approximating curve instead of a straight line. The simplest of those is a parabola. Let's call it t of x. A general formula for the parabola approximating a function f at the point A is a plus b times x minus a plus c times x minus a squared. What properties does this parabola need to fulfill in order to be a nice approximation of f in the neighborhood of the point A? First of all, we need that the values of f and t in A are equal. Also, the slope of t at A should be equal to the slope of f at the point A, so that derivative should be the same at A. And finally, to ensure that t follows the curvature of f, the second derivative should be the same at A. Collecting this information about t, we get the following equations. Solving those for a, b, and c, we get the coefficients of the parabola we are looking for. Here we go. From equation 1, we find that a equals f of a. From equation 2, we get that b equals the third derivative of f in a. And equation 3 gives c equals half times the second derivative of f in a. The formula for the parabola t of x is now f of a plus f prime of a times x minus a plus half times f double prime of a times x minus a squared. It is interesting to see that the first part of t of x is exactly equal to L of x, the linear approximation of L in A. This is not a coincidence. In fact, we can refine this method and find approximated polynomials of higher and higher degrees. These polynomials are called Taylor polynomials. This is the formal definition of Taylor polynomials. F of a plus the derivative of f in a times x minus a plus 1 over 2 times the second derivative of f in a times x minus a squared plus so on till 1 over n times n minus 1 till 2 times 1 times the n derivative of f in a times x minus a to the power n. We see that this is a sum of n plus 1 terms. We can write this in a shorter form. For this, write the product of all n descending numbers from n down to 1 as n exclamation mark. This is pronounced as n factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1. And n factorial is equal to n times n minus 1 times n minus 2 up to 2 times 1. Then we can write the expression for the n Taylor polynomial as follows. The sum of k is 0 to n of the k derivative of f in a divided by k factorial times x minus a to the power k. The polynomial t subscript n has the special property that the k derivative of t subscript n x and f of x in the point a are the same for k is 0, 1, 2, up to n. Now let's go back to the square root of 4.05. Let's use a second order Taylor polynomial to approximate its value. We take for f of x the square root of x. We also have to choose a point a in the neighborhood of 4.05 that is easy to compute with in a square root setting. 4 will do the trick, because the square root of 4 equals 2, which is easy enough, right? The formula for the second order Taylor polynomial t subscript 2 is now f of 4 plus f prime of 4 times x minus 4 plus half times f double prime of 4 times x minus 4 squared. Let's see. What do we need? In the formula for t subscript 2, we need the first and second derivative of f of x equals the square root of x. The first derivative is 1/2 times x to the power minus 1/2. And the second derivative is minus 1/4 times x to the power minus 3/2. So here we go. F of 4 equals 2. The first derivative of f in 4 equals 1/2 times 4 to the power minus 1/2 equals 1/4. And the second derivative of f in 4 equals minus 1/4 times 4 to the power minus 3/2, which is equal to minus 1/32. Filling these numbers in gives us the explicit formula for t subscript 2 on the screen. The square root of 4.05 equals f of 4.05. Since 4.05 is close to 4, f of 4.05 is approximately equal to t subscript t2 of 4.05. Filling in x is 4.05 in the formula for t subscript 2 of x yields what you see on the screen. A scientific calculator gives easily the first 10 decimals. We see that our approximation is correct up to 5 places of decimals. If you want to make a further improvement to this approximation, we take t subscript 3 instead of t subscript 2. In fact, this is what your calculator does, using Taylor polynomials of a higher degree to get a better approximation.